is Chapter 9 Assignment Video Problem Number 1. Chapter 9 deals with correlation. We're trying to decide if two variables are correlated. For example, I feel that the number of hours that you study is correlated to your test grade. So I feel that the more hours you study, the higher your test grade is. I feel that those are correlated. Now that would be positive correlation because those values are both going in the same direction. As one goes up, the other goes up. That's positive correlation. Now we also have negative correlation, and that's when things are going in the opposite direction. So that might be something like the number of times you check your phone and your test grade. So I feel that the more times you're distracted by your phone, the higher number of checks there are on your phone, the lower your test grade is. So those are going in opposite direction, but I do feel that they are negatively correlated. So things that go in the same direction are positively correlated. Things that go in opposite are negatively correlated. Now we have to decide if it seems like there's some correlation going on here, but is it strong enough? So R is a value that we use to test the strength of correlation. Now we have a couple of ways that we can decide if there's correlation. We can look at R and we can look at a p-value, and we're going to do both of those methods here in a moment. But what I've already filled in here on the problem is that we set these up like a hypothesis test. So we have a null and the alternative hypothesis. And every single one that we do, it's always that rho is 0. Now rho stands for the population linear correlation coefficient. So if rho is equal to 0, that means there is no correlation. That it's 0. There's no correlation whatsoever going on at all. Now, if rho is not 0, if we get anything other than 0, there is some correlation going on. However, we have to decide, is it strong enough? And we do set a significance level ahead of time at, how strong do we want the correlation to be for us to say that there is correlation. So this is set at 0.05, our alpha significance level. So what we do is, let's go ahead and go through the hypothesis test to see if we have correlation or not. I went ahead and put this into StatCrunch, and here is the murders in this column, and this is the population. So we have 11 pairs of data going on. So we're trying to figure out if there is a correlation between the number of murders in a large city and the population size in a large city. Is there correlation going on there? So the way we do that in StatCrunch is we enter the data first, then we go to Stat and Regression, Simple Linear. And we tell it to look var1 for the X and var2 for the Y. And we simply hit Compute. And the first thing I like to do is I like to look at the scatter plot that StatCrunch makes for us. If you click on this arrow right here, it shows you the scatter plot. So what we have is there's 11 dots on the graph because we have 11 pairs of data. So what this dot represents, if you hover over it, it tells you what it is, but it looks like it is the pairs of data right here, where we have 60 murders in a city and a population size of 700,000. So that's what that dot represents. And so we have 11 dots, and it looks like the trend is going up. We have this line of best fit that StatCrunch calculates for us that is showing us that this is the trend to the data. As this value increases, this is the number of murders increase, the larger the population. So this is positive correlation. So we know we've got some correlation going on. We just have to decide, is it strong enough correlation? And that's what we measure with the correlation coefficient R. So we take a sample, here's our sample, to make some sort of inference about the population as a whole. So we're going to look at 11 pairs of data. We didn't look at every single city, but we looked at 11 cities. And based on this sample, we're trying to make some sort of hypothesis about all cities, murders in all large cities and the population size of all large cities. So that's what we're trying to do. So this is rho because the hypothesis we're making is about the entire population. But R is about our sample. So R is how strong is the correlation of our sample. Now, if we got 0 here, that would mean there's absolutely no correlation. If we get something other than 0, then we know that we do have some sort of correlation going on. We just have to decide how strong it is. So where do we get that number? Right here, R is the correlation coefficient. This is where we get that. So we have 0.7143. Now, this is getting close to 1. So R, a strong positive correlation, it would be an R value of 1. That's the strongest correlation you can get. Strong negative correlation is an R value of -1. That's perfect negative correlation. So what we think about is R going on a continuum from -1 being the strongest negative correlation, to 0 being no correlation, to +1 being very strong positive correlation. But we need to know where's this cutoff value. Like, where do we say, somewhere along here, we're going to say, yeah, it's far enough away from 0 to say that we have correlation. Now, that value is called a critical value. The critical value is based on what alpha is, and we get this from a table. Now, you will be given a table like this when you take your test, but you can also find it in Brightspace for that unit. It's also in your e-text that you can access through My Stat Lab. So I'm going to drag that over here. And this is the table. And the way you read this is you figure out what your significance level is. So it's 0.05. And then N stands for your number of pairs of data. So for this example, we had 11 pairs of data. This is my critical value. Actually, we have a positive and negative. So let's see what that means. Let's go down here. I'll write it down here first. So our critical values are -0.602 and positive 0.602. Let's go down here. Here's our continuum. We need our cutoffs. Based on alpha being 0.05, where is the cutoff for saying that we have significant linear correlation? So it's going to be somewhere right here. This is positive 0.602, and down about right here would be negative 0.602. So what that is it's giving me a region here in red. If we get an R value that's in either one of these regions, then we know that we have significant linear correlation. You know, anything other than 0 is correlation, but it's not strong enough correlation to be evidence unless it's in this region. So anything in here we would not have, there would be no correlation, we would say. I mean, there's a small amount, but we'll say no significant correlation in the blue area. Anything in the red, this end or this, and this would be strong negative correlation. If we get an R value in this area, it would be strong positive correlation. So R, we calculated that already. R was came from StatCrunch, came from this right here. So let's see where R is. R, if this is 0.60 and this is 1, R is going to be about right here. Here, let me put that in blue. R is going to be, it's not drawn in really good, right here. This is R, which is equal to 0.7143. So it is, we do have strong linear correlation. R is in this red area, that correlation area. So we do know that we have significant linear correlation by the first method. And the first method is using critical values in R, okay? And there's another way to decide if we have correlation. The second way is looking at the p-value. So the p-value comes from StatCrunch. And let's take a look at where we get that. We look here, there's a lot of data here, but we're looking at this row that says slope. This 3.06 value is the test statistic, which gives us a p-value. So the test statistic is computed from our sample. The test statistic gives us the p-value. So we'll just write those down, what we got. Our test statistic was 3.0623, and the p-value, which is what we look at, is 0.0135. Now, just like in hypothesis testing, if we get a p-value that is less than alpha, then we have a significant linear correlation. So our second method down here is the p-value less than alpha? Yes, it is. 0.0135 is less than 0.05. So we do have significant linear correlation. If we do use this method, we have significant linear correlation. It's actually positive correlation. And if you look at this method, we have significant linear correlation. So what that means is, this is a hypothesis test. So just like in Chapter 7, we are making a decision on, do we reject the null or not? So since we did get evidence, we're going to reject the null. The null is saying that there is no correlation. We're rejecting that because we got evidence of correlation. So we are going to say that we reject the null hypothesis. What does that mean? What's our concluding statement then about correlation? What does that mean? So what we would say is, we would either say there is evidence or there is not evidence. And this is the same for every problem that you'll do. There is evidence at the 0.05 level of significance to suggest I need to add the word here, a positive linear correlation between murders and population. Now I know that it's positive correlation, one, because I looked at the graph and it's going up, so it's positive. I also know that it's positive correlation because R is positive. Now the next part of this is actually what we learn about in section 9.2, is this regression equation that we can get. Now if you remember back from algebra, lines have an equation. We can get in the equation of this line here. And StatCrunch computes all of that for us, makes it very easy. And it's right here. This is the, actually in algebra we called it the slope-intercept form. But this is the equation of the line that's given in StatCrunch there. So I'm just going to jot that down. And this is how we write it. It's written here. You can go through your notes for a little more explanation about this, but it's saying var1, which is y, is equal to negative 7.6 plus 0.079 times var1. We usually use this notation here, though, to say that our y hat, that's our y variable, and we use the hat to say that this is just an estimate, but y hat, which is the murders, the y hat, if you look up here, is our population values. So the way we're going to get that is going to be equal to the negative 7.6324 plus 0.0795 times x. So our x's is our var1, which is the murders, and this y value is our population, which is, we have that in var2 in StatCrunch. So here's the equation of the line that we're going to use, and what we do with that is we can make predictions. So this question says here, find the population size of a city that has 342 murders per year. So we've established that we have correlation. This is the regression equation that we can use to figure this out. So simply what we do is, this 342 number is murders. We are going to plug that in here where x is, and we'll do the computation here, and that's going to give us the population size. So we will say that our population size is equal to negative 7.6324 plus 0.0795 times x. So I'm just going to use this in red. just to highlight that we're substituting the 342 in where X was. And again, this comes straight from StatCrunch. This comes from this right here. So when you do this math over here on this side, you're going to get, that's going to be equal to 19.6 100,000 people. So this is a population, 19.6, that's in hundreds of thousands. All right. Now the next part of this question says to find the population size of a city that has 1,000 murders. So you're probably thinking, oh, well, we'll do that just like we did this one. We'll plug in 1,000 right here. However, this is a little bit different because this value here is well outside of all the other values. Let's go back and look. Here's all of the X values that we had. We had a low here of 60 murders and a high of 648. So this 342 number that we use down here in this example is within the range of all the other values. However, this value is not. So we won't use the regression equation in this example here, just because it's so far out of the range of the other numbers that we don't say that it's meaningful to use the regression equation. But we still have data, and so we still can estimate it. And all we simply do is we find the mean of the population sizes in this data set. So we can't use the regression equation. We're just going to find the mean. We're just going to find the average population size that we have from these 11 pairs of data. So we call that y-bar. And the way to do that, I'll show you in StatCrunch. So here, maybe I'll make you a little note here that this is too big to use regression equation. All right, so we're just going to find the mean instead. So we use the mean for this is going to be called y bar, just like x bar was sample mean. We're going to call this y bar, and it's just the average of all our y values. So let's go back to StatCrunch, and StatCrunch can do this real easily for us. Here's all my y values. I just need the mean of all these values here. And the way we do that is just stat, summary stats, columns. And we want to tell it to look in var 2, because that's the population size, and you hit compute. Now there we get that the mean is 19.7272. So that's close to, let's see, write this down here. So 19.7272. Actually, that would round to 3. So that's our best way to estimate the population size of a city that has 1,000 murders, is just to find the mean.